discuss about a special diode known as Zener diode. Now, this Zener diode is very much used in voltage regulators to maintain a constant voltage across a varying load. Now, in order to understand our Zener diode operation, let us first again recall the VI characteristic of a PN diode. So, the VI characteristic of a PN diode, as you can see here, it is in two regions. One is the forward biased and the other region is the backward reverse bias. In the forward bias region, the current rises sharply after crossing the threshold voltage, which is around 0.7 volt for silicon and 0.3 volt for germanium. Now, let us concentrate in the reverse bias condition. So, when the reverse bias voltage that is applied across the PN diode is increased, current does not increase significantly. So, the whatever little current flows, that is called the reverse saturation current IS, and this is due to the minority carriers present in the diode. Even though we increase the reverse bias voltage, the current does not rise significantly. Now, if we go on increasing the reverse bias potential, then if it is sufficiently large, after a point we see that there is a sharp increase in the reverse current IR. That means, here the voltage which is to be reached before the breakdown condition, that voltage is known as the breakdown voltage, and the breakdown in a PN diode occurs generally due to two phenomena. One is called the avalanche breakdown, that is because when the applied reverse bias potential across the diode is very large, then the electrons, they get sufficient energy, sufficient kinetic energy to break open the covalent bond, and in the process they release other electrons, and these electrons also get energy to knock out other electrons from nearby covalent bonds. So, this process is actually a cumulative process. So, there will be an avalanche of carriers present, and that is why there is a large rise in the current, and this process is the avalanche breakdown. But this avalanche breakdown phenomenon generally happens for lightly doped PN diodes. Now, if we increase the doping concentration in P and N type, then we can get the breakdown occurring at even a lower potential. So, if the doping is high, then we could get the breakdown occurring as low as at even -5 volt. So, that phenomenon for a heavily doped diode is known as Zener breakdown. Now, there is a fundamental difference between avalanche and Zener breakdown. Now, what is Zener breakdown? Because of the reverse bias potential being high, there will be a strong electric field present across the junction. Now, due to this high field intensity, the rupturing of the covalent bonds will occur, and that is why whole electron pairs will be generated. So, here tearing of the covalent bonds occurs because of the high electric field across the junction, because of the application of a high reverse bias potential. So, this breakdown is called Zener breakdown. Now, this Zener breakdown will be having a sharp rise of the reverse current in the diode. That means, this current will suddenly very sharply rise after crossing this Zener breakdown voltage Vz. So, the major reason for the Zener breakdown is that because of the rupturing of the covalent bonds. So, now this breakdown potential V Z can be brought to lower levels by increasing the doping levels in the p type and n type materials. So, these Zener diodes exploit this breakdown phenomenon, which is effectively used for some special applications. For example, a common application is the voltage regulator. Now, this Zener diode is manufactured with adequate power dissipation capabilities, so that they can operate in the breakdown region, because the normal diodes we cannot operate in breakdown region because of this danger of degrading the characteristic of the diode if the power dissipation capability is not high, and normal diodes do not have the high power dissipation capability. That is why it is dangerous to use in the breakdown region, but the Zener diode have higher power dissipation capability, so that they can be used in the breakdown region without any danger of degrading their properties. So, these Zener diodes are some special diodes which is effectively utilized in the reverse breakdown region. Now, it does not mean that the Zener diode is only operable in the reverse breakdown, but it can be used in the forward region also. In the forward characteristic, if we see, it will be similar to the VI characteristic of normal diode. So, if we consider now the VI characteristic of the Zener diode, in the forward region you see that the current versus voltage is like a normal diode. So, in this region we can equivalently express the Zener diode by a source 0.7 volt across this diode, which is due to the threshold voltage, and the resistance of the diode, which is very small in the forward bias condition. So, this Zener diode in this region with plus across this P and negative of the terminal of the battery across the N of the diode, that means it is forward bias condition. So, we have the equivalent circuit for this Zener diode in the forward bias condition is like a normal diode having 0.7 volt drop across the diode, and resistance RZ is the resistance of the Zener diode in the forward bias condition. But as this RZ is very small, we can effectively equivalently express this equivalent circuit by another approximation, keeping the 0.7 volt battery that is expressing the voltage drop across this diode. So, this equivalent circuit is having this voltage drop 0.7 volt for silicon, and this characteristic in the forward bias condition is similar to your normal PN diode. But now, let us concentrate in the reverse biasing condition. So, now when the reverse bias voltage is low, even in the case of increasing the reverse bias potential, the current will be low, because this current, which is the saturation current, is due to the minority carriers only. So, the current is very small, and in this region, even if you go on increasing the potential, we will not be getting rise of current. If we go on increasing the reverse bias potential even further, then we will see that after a point the current is rising sharply, but the voltage is almost same. that is the voltage is maintained constant, but the current is rising significantly. That means here the Zener breakdown is occurring. So, till the point when the breakdown does not occur, this region, as it is having very less current, the resistance in this portion is very high. That is very clear if we find the slope of the curve, and in inverse or reverse of this slope is the resistance. So, the current change is very small, even though change of this voltage is very high. That is why we infer that the resistance is very high in this region. So, this Zener diode in the reverse bias condition, the negative of the terminal of the battery applied to the Zener diode is connected to P and N connected to positive. This is the symbol of the Zener diode. It is a crooked N to differentiate it from the normal Pn. So, this region can be equivalently expressed by only the resistance, which is very high. So, as the current is almost 0, if we ignore this minority current, which is very small, we can approximate it as an open circuit, that is current is almost 0 in this region as compared to the current which flows after breakdown. So, when this point of breakdown is reached, after that point the current rises very sharply. So, this is almost a linear region. So, the slope of this region, inverse of this slope will be giving the resistance. That resistance is very small, only a few ohms after breakdown. So, this resistance, dynamic resistance is given by del Vz by del Iz. If we consider two points in this region, find out the change in the voltage and corresponding change in the current, we will see as this curve is almost vertical. So, the change of voltage is very small, but the change of current is very high. So, the resistance will be very, very small. So, dynamic resistance which is obtained in this way is very, very small. So, in this region, as this voltage across this diode is almost constant, we get a constant voltage, and apart from that constant voltage across the diode we have a small resistance. Now, there is a point called the knee current in the current axis. If we see, the current Izk is the knee current, and what does it mean? Actually, if we consider the knee region of this curve, center of this knee region is corresponding to this point Izk. That means below this knee current there is no breakdown. That means from this point to this point up to the knee point, this resistance is very high and it is almost like open circuit. This Zener diode is almost like open circuit, and the corresponding voltage is Vzk for this knee point. The center of this knee point is corresponding to Izk, Vzk. Actually, that point is significant in the sense that before this point is reached, the reverse breakdown phenomenon is not occurring, and the Zener diode is only having the reverse saturation current, which is very, very negligible. So, the resistance is very, very high. After this knee point is overcome, after this knee point is reached, this current is rising very sharply. So, if we extend this linear region of the graph, it will be intersecting the voltage axis at a point Vz0. This Vz0 and Vzk, this difference is very, very small and it is almost, these 2 points are very, very close. Now, if we take any point on this reverse breakdown region and find out what is the voltage at this point and the current at this point. For example, we are taking this point which has a current Iz and a voltage Vz. Now, this voltage Vz actually is the voltage Vz naught plus this region, this voltage. So, this voltage is nothing but Iz into Rz, that is the drop in the Zener resistance. So, Vz naught plus Iz Rz will give you the voltage across the Zener diode at that point of operation. So, we can now consider the Zener diode in the reverse breakdown as having a voltage drop which is Vz naught and having a resistance Rz. So, the overall voltage drop across the Zener diode is Vz, which is equal to Vz naught plus Iz into Rz. Now, again Rz is very small, because this linear portion, if we consider this resistance, if we find out, it will be very small, as there is very less change of voltage for a considerably large change of current. So, we will be not wrong if we approximate it to have only the voltage drop Vz naught and ignore this part Iz into Rz. This drop will be very negligible. So, ultimately we have this model of the Zener diode in the reverse breakdown condition as having the voltage Vz, which is equal to Vz naught. So, this part can be neglected. So, what we get across this Zener diode after Zener breakdown has occurred is that a constant voltage drop Vz is maintained, even though current can change. So, this particular phenomenon is very effectively utilized, that we will see later. So, once this reverse breakdown occurs, then the voltage across the Zener diode will be locked at the voltage Vz. Now, this Vz, that is the Zener voltage for Zener diodes, is specified in the data sheet for a particular Zener diode that you are using. So, it can be around say 3.9 volt Zener diode also we can have, and it may be even brought further less, and higher voltage Zener diode also are available. So, there will be a variety of Zener diodes having different Zener voltages, which will be known from the data sheet. The Zener diode you are particularly using, how much is the Zener voltage, that will be specified in the diode. Apart from that specification, another specification which is very important is the power dissipation. That is, the Zener is having a particular maximum power dissipation capability, that is also specified in the data sheet. So, for a particular Zener diode, what is the maximum power that is able to dissipate, that rating will have to always be remembered, because we cannot exceed that power rating. So, one rating is the voltage Zener voltage and the other is the power dissipation. These two are important parameters of the Zener diode which are specified in the data sheet. So, keeping these two parameters in mind, we have to design Zener circuits for regulation or for other purposes. So, when you use practically these 2 points, that is the Zener voltage and the power dissipation are to be kept in mind, and this power dissipation is higher than compared to the normal diodes, because the Zener is particularly designed for use in the reverse breakdown condition. So, it will be having a higher power dissipation than the ordinary or normal PN diodes, which are generally operated in the forward bias condition. So, now after this we now can see that the voltage across the Zener diode will be locked to a voltage which is specified in the data sheet, that is known as the Zener voltage or breakdown voltage, and along with it the power dissipation capability of the Zener, maximum power dissipation rating, that is also specified. So, the symbol of the Zener diode is this one. So, this P and N is a little tilted than the normal diode symbol, and we always operate the Zener diode generally in the reverse breakdown. That is why plus of the battery terminal is connected to N, negative of the battery terminal is connected to P, and this voltage Vz is specified and the current flowing through the Zener diode is Iz, and you have to notice the direction of current because the Zener diode will be reverse biased, positive of the battery terminal will be connected to N. So, the current direction will be the conventional current direction from positive of the battery terminal to the negative. So, that is why the current direction is Iz as is shown in the diagram. So, this is the symbolic representation of the Zener diode. Now, as we have seen and understood in the Vi characteristic of the Zener diode, in the reverse breakdown condition we approximately model the Zener diode as this circuit having the voltage drop Vz naught, along with it there is a resistance Rz in the reverse breakdown. So, basically the voltage across the Zener diode Vz is equal to Vz naught plus Iz Rz. So, if Iz varies, this drop is variable. This part is this Vz naught is constant because this is the point where the linear characteristic intersects the voltage axis, but for different operating point on the reverse breakdown this current Iz will vary. So, the drop Iz Rz will also vary. That is why basically the whole drop is Vz naught plus Iz Rz, but as this Rz is very small, this whole drop Iz Rz which is exactly actually variable, we can approximately ignore this drop, since as this Rz is small, this drop will be small. So, this variable drop can be neglected altogether, and then we will be having Vz equal to Vz naught. That is the practical model which is used for Zener diode in reverse breakdown, that is equal to Vz, this drop is equal to Vz naught. So, this is the approximate equivalent circuit, and this circuit will be frequently and mostly used unless and until you are specified that you have to take into consideration that resistance also, but for our discussions we will be generally neglecting this drop. So, this Vz is a battery, like it is shown like a battery. So, this drop is constant, that is why it is shown like a battery, that is the drop across the Zener. Now, the voltage Zener voltage or the breakdown voltage is sensitive to temperature also. So, the temperature at which you are operating the Zener diode has an effect on the breakdown voltage. That effect is generally expressed by temperature coefficient Tc, and this temperature coefficient is used to find the change in the Zener voltage Vz or breakdown voltage Vz, which arises due to a change in the temperature of operation. So, the expression which is used to find out this temperature coefficient is Tc is equal to del Vz by del Vz by Vz divided by T1 minus T0 into 100% per degree centigrade. So, what is this del Vz? This is the change in Vz due to temperature change. T1 is a new temperature level and T0 is the room temperature. Generally, this is nominal temperature at which we do our calculations. This is 25 degree centigrade, room temperature is taken as nominal temperature, and at that temperature 25 degree centigrade the Zener voltage is Vz. So, if we have a change from 25 degree centigrade, that is T1, and with this expression we can calculate what is the change in Vz from the nominal Vz, that is the voltage Zener voltage at 25 degree centigrade. From that what change occurs due to the change in temperature, that can be calculated from this, and if we know del Vz we can find out what is the new Vz, that is equal to old Vz plus this delta Vz. So, temperature has an effect on the Zener voltage. Now, main application of Zener diode, as I have indicated, it is in voltage regulator circuits. So, a voltage regulator is a combination of elements which are designed to ensure that the output voltage of a supply remains fairly constant. And if we recall the rectifier circuits which we discussed earlier, we had a block diagram representation which gave the various stages of rectifier circuits. So, starting from a sinusoidal AC voltage, we first of all rectified it using half wave or full wave rectifier, which is with a capacitor filter to smoothen out the DC voltage. But finally, what we got, even after using the filter capacitor, we got a DC voltage which had ripples. These ripples are present in the DC voltage that can be removed if we now use a Zener regulator. That is, finally, after rectifying it with filter capacitor, we can further rectify and find a final constant DC voltage if we use a Zener voltage to maintain a constant output voltage. So, finally, we can get a constant output voltage from the DC having ripple part. So, how that is obtained? The main principle is that Zener diode is a diode which is used in the reverse bias condition, where after breakdown the voltage across the Zener diode locks to a constant voltage. That principle will be used. So, we will see that even if there is a change in the load current or there is a change in the input voltage, we still get an output voltage which is constant. So, we will be first considering the basic Zener regulator circuit, a simple basic circuit just to show how this regulation of voltage occurs. We will be taking help of a simple circuit. So, in this circuit, both input voltage and the load resistance are first of all kept fixed. Let us first discuss how the regulation takes place, and then we will be going to practically what happens when the input voltage and load resistance changes. So, here for this case, let us start with constant voltage Vi as the supply voltage to this circuit, and the load resistance RL is fixed. Now, this circuit has this Zener diode, Vz is having Zener diode is having its constant voltage Vz after breakdown, and maximum power dissipation capability is Pzm. These are specified in the Zener diode. This R is there to limit the Zener current after breakdown. This is called current limiting resistance. It is in series in the circuit. It will be limiting the Zener current which flows enormously after breakdown, and that can be limited by using a resistance in the circuit. So, if we study this circuit now, first of all we have to find out that condition under which the breakdown in the Zener diode occurs, that is when the reverse breakdown will be occurring. When the voltage across this Zener diode, that is the load voltage, is greater than or equal to the limiting condition, the Zener voltage, at that condition the Zener will be breaking down, reverse breakdown will occur. So, first of all in this circuit we must ensure that the voltage applied across this Zener diode is greater than or equal to the Zener voltage. Now, what is the voltage that is across this Zener diode? That has to be found out. So, to find out the voltage across this Zener diode, we will be using Thevenin's theorem, open circuit this diode and find out the voltage looking from these two terminals. So, next step, we are from this diode, we will be removing this diode, open circuiting this, find out the Thevenin's voltage V Thevenin across these two terminals. That is the way we have to find out the voltage across the Zener diode. So, first of all let us find out V Thevenin. What is V Thevenin? So, this voltage across these 2 points after open circuiting this diode using Thevenin's theorem, the voltage across these 2 points is Vi into RL by R plus RL. that is the voltage division is taking place across these two resistances. So, this voltage we will be finding out. Now, if V Thevenin, this voltage is greater than equal to V Z, that is the Zener breakdown voltage for this particular diode which we are considering, then the Zener diode will be in the on condition, means breakdown will occur, and we can approximately replace this Zener diode by its approximate equivalent circuit. Now, if this voltage across this Zener diode, this open circuited voltage V Thevenin is less than V Z, then the Zener diode will be not on. So, first of all we must ensure whether the Zener diode is on, that means whether breakdown is occurring or not. That means we must first ensure that the open circuited voltage across the Zener diode must be greater than the Zener voltage for that diode. So, now if this condition is met, that is V Thevenin is greater than equal to V Z, then we will be replacing this circuit by its equivalent circuit, which is nothing but a drop V Z. This source or battery is expressing that a constant voltage drop V Z is occurring across this Zener diode after breakdown. So, substituting this equivalent model, now we get this circuit, it is an electrical circuit. Now, we can find out the different currents and voltages in the different components of the circuit. So, the voltage V Z is constant, even though currents may change, that means the current I L may change if we change the R L, but V Z will be constant. But for in this case we are keeping this R L constant. What is the voltage across this R L? That is V L, load voltage. This voltage at these 2 points is nothing but this voltage V Z. So, V L is equal to V Z. Now, at this point we can now apply the Kirchhoff's current law. So, the algebraic summation of the currents at this node equal to 0, that is Kirchhoff's current law. So, using Kirchhoff's current law, all are outgoing currents I Z plus I L are outgoing, I R is incoming. So, incoming current is equal to sum of the outgoing currents I Z plus I L, I R is equal to I Z plus I L. Now, you can find out what is I Z, the Zener current, that is equal to I R minus I L. Now, what is I L? Load current, V L by R L, V L is nothing but V Z. Now, we will be also able to find out what is I R. The current flowing through this resistance R A is nothing but the potential across these 2 points divided by resistance. Now, potential across this at these 2 points, difference of potential across these 2 points is V I minus V Z. So, V I minus V Z divided by R is I R. And after knowing all these currents and also we have known the voltages across the different components, we can also find what is the power dissipated by the Zener diode. So, the power dissipated by the Zener diode is the product of the voltage and current flowing through it. So, PZ equal to Vz is the voltage across this Zener diode and current flowing is Iz, Vz into Iz will give you the power dissipated in the Zener diode, and it should be less than the maximum power dissipation capability of the Zener diode, which is equal to I PZM. PZM is defined. What will be that value? You know that. So, PZ should be less than PZM. This is a case where you did not have a variable voltage or a changing load. But now, let us consider the variable load and fixed Vi, that is the voltage is kept constant, input voltage or supply voltage Vi is kept constant, but the resistance is variable. You change the resistance, you can change the resistance and consequently you can change the load current. That type of a circuit let us consider. So, now in this circuit this load is variable, that is why it is a variable symbol is used for this load resistance RL. Now, how much variation can this load resistance have in order to turn the Zener diode on? Because you can change this load resistance, how much change you can make? how much minimum value and up to what maximum value we can change the load for Zener diode to turn on, because there will be a range. You cannot go on arbitrarily changing the load resistance, that will be clear, because the first and foremost condition to be satisfied is that the voltage across the open circuited voltage across the Zener diode must be greater than Vz. So, that will be putting a limit on RL. Now, what will be that RL? Maximum and minimum values, let us go to find out. If we change this load resistance to very small value, we will be having a Thevenin's voltage across this Zener diode which will be less than Vz, and then the Zener diode will be off. So, first of all let us find out that minimum load resistance RL which will turn on the Zener diode. So, assuming that the Zener diode is turned on by that resistance RL minimum, what will be the minimum value of RL? So, in order to calculate that value of RL minimum, let us consider the Zener diode on and find out. So, if Zener diode is on, for this VL will be equal to Vz. So, what is this voltage across this Zener diode? Thevenin's open circuited voltage is Vi into RL by RL plus R, and that must be equal to Vz. Actually, it is greater than Vz, but let us take the limiting condition to find out that limit. So, VL is equal to Vz equal to Vi into RL by R plus RL. So, if we simplify this expression and solve for what will be RL, then we get that value of RL is equal to Vz into R by Vi minus Vz. That means the resistance value should be at least equal to Vz into R by Vi minus Vz. We are not changing R is constant. Once you design R, we are not changing. Vz is the voltage, Zener voltage for that particular Zener we are applying. Vi is constant. So, this expression will give you the minimum RL which will make the diode, Zener diode on. If it is less than that, this voltage will be not sufficient to make the Zener diode on. So, you should have any load resistance greater than this value of RL minimum to make the Zener diode on. Now, that RL when it is minimum, if we again concentrate and think about this condition of Kirchhoff's current law at this node. Now, if this IL is maximum for that condition of RL minimum, this Zener diode will be this RL is minimum, this RL is minimum and IL will be maximum. So, when IL is maximum, that IZ will be minimum, because IR equal to IL plus IZ. So, now this IL is maximum because we are having a load resistance which is minimum. So, IL maximum will make IZ minimum because IR is constant. So, we have now a condition for IL maximum which is obtained VL by RL, that is equal to Vz by RL minimum, the minimum resistance which we have just now derived, that will be giving you the maximum load current and that will be giving you the minimum Zener current. So, what is the IZ minimum that we can find out, because IZ minimum is equal to IR minus IL maximum, and what is IR, that we know, IR is equal to this current is equal to Vi minus Vz by R. So, this is one condition where you will be getting the maximum load current, correspondingly minimum Zener current. Now, let us find out the maximum load resistance. Now, when you have maximum load resistance, then load current will be minimum, because IR is equal to I Z plus I L, when R L is maximum, this I L is load current is minimum. So, as load current is minimum, I Z is maximum, but I Z has a rating, maximum Zener current is specified in the diode. So, that maximum Zener current I Z will be causing load current to be minimum. So, what is that minimum load current? IR minus IZ max. Now, corresponding to this minimum load current, we have the RL max, that is equal to VZ by IL minimum. So, because if you look into this circuit, VL by RL minimum is IL maximum, as well VL by RL maximum will give you IL minimum. So, IL minimum will give you IZ maximum. So, this IR we know, because IR is equal to Pi minus Vz by this load, this resistance R. So, once you fix this IR, we can find this maximum Zener current. So, maximum Zener current means IL minimum. So, you have now obtained conditions for RL minimum and RL maximum. So, within this range you can vary this load resistance to get a constant Zener voltage, and this maximum condition we will be getting from the Zener current maximum rating of the diode. Now, another condition may happen when the input voltage Vi is variable, but RL is fixed. Suppose supply voltage is variable, then in order to find out Vi minimum and Vi maximum rating, how much change can be allowed for the input voltage Vi or source voltage Vi in order to get a constant voltage drop VL, that is the problem. Now, this Vi, in order to find the minimum condition, how much small Vi may be in order to turn on the Zener diode, that condition we will be finding out from the fact that Vi must be sufficiently large to cause the Zener to go into the breakdown state, but that will be found out from the voltage across this Zener diode, which is Vi into RL by R plus RL, that must be greater than Vz. So, putting the limiting condition, here we get VL is equal to Vz is equal to Vi into RL by R plus RL, assuming that the Zener diode is on. For Zener diode to be on, what will be the corresponding VL, VI that we are finding out. So, Vi minimum is equal to, cross multiplying from this expression we get, this is equal to Vz into R plus RL by RL. So, minimum value of voltage input must be this one. And what about the maximum value of Vi? How much you can go on increasing Vi in order to make the Zener diode on, with keeping within the limit of the Zener diode specification, because we have a maximum Zener current rating. If you go on increasing Vi, Zener diode current will be going on increasing, but we cannot go on increasing so much because there is a limiting condition which is specified in the data sheet of the Zener diode given by IZ max. So, for that IZ max, what will be the IR max? That is maximum current IR will be IZ max plus IL, since this voltage is constant, resistance also constant. So, VL by RL is constant, we are not changing the load. So, IL is constant. So, IR max is equal to IZ max plus IL. So, as IL is fixed, so maximum Vi is equal to VR max, that means the voltage across this resistance, maximum voltage across this resistance plus Vz. Maximum voltage across this resistance means when maximum IR flows, that is IR max into R. So, IR max into R plus Vz will be the Vi max. What is IR max? IR max is equal to IZ max plus IL. IZ max is given by the specified data sheet. So, we have a limiting condition on Vi max. So, Vi mean Vi max, we have found out those condition. RL max, RL mean also we have found out. So, with the variation in Vi or the variation in RL, still we are able to maintain the voltage across the load at a constant voltage Vz, and that is the usability of this Zener diode. Where we find the effective use of this Zener diode is this type of problem, where you want to maintain a constant output voltage, that is in voltage regulator circuits. Now, let us try to solve an example. Now, in this circuit utilizing Zener diode, you are having the input resistance Ri, that is in the series resistance connected in the circuit, is 222 ohm. The Zener diode is having a Zener voltage of 10 volt. This is the load resistance RL, which is a fixed load resistance, it is not varying. The input voltage is also fixed at 20 volt. Now, given that maximum power rating of the Zener diode is 400 milliwatt, maximum Zener diode rating is specified. You are to find out in part A the current IL, load current, Zener current Iz, and this current through this resistance Ri, the current I, if the load resistance is given as 380 ohms. And part B, to determine the value of RL, that will establish the maximum power Pz max in the diode. That is, what resistance RL will cause this maximum Zener power 400 milliwatt, maximum power dissipation. So, in order to solve this two problem, first part of the problem you have to find out this current IL, Iz and I. So, before finding out the currents, we must first ensure whether the Zener diode is turned on or not. That is, whether breakdown is occurring in this Zener diode or not, that has to be found out. So, for that we will be proceeding to find out the open circuited voltage across this Zener diode, Thevenin's voltage, which is 20 volt into RL by RL plus Ri. So, our next step is find this Thevenin's voltage across this Zener diode. So, this voltage we will be finding out after open circuiting this Zener diode. So, next we will be open circuiting these 2 points. Here this is the resistance Ri and this is the voltage 20 volt, and across these 2 points what will be V Thevenin? You have a resistance RL. Now, this voltage is nothing but 20 into RL by RL plus Ri, and that is equal to 20 into 380, RL is 380 by 220 plus 380, that comes to 12.67 volt, and our Zener diode is having a Zener voltage of 10 volt. So, definitely it is greater than Vz. So, the Zener diode will be turned on, breakdown will occur. So, the Zener diode will turn on. So, if the Zener diode turns on, this voltage across this Zener diode will be locked to the voltage 10 volt Vz. So, this voltage is constant. So, this loaded voltage VL is also constant. So, we can very easily solve this currents. For this currents, if we want to find out first of all what is this current I. So, this I is 20 minus 10, this Vz is now 10 volt, it is locked. So, 20 minus 10 by Ri, 222 ohms, that gives 45 milliampere is the current flowing in this circuit I current. So, I is equal to 45 milliampere. Now, what about this current IL? IL is equal to the voltage across this load resistance, this voltage across this load resistance by load resistance RL is the IL current. Now, what is this voltage? After Zener breakdown, this voltage is constant at 10 volt. So, this voltage is also 10 volt. 10 volt divided by load resistance 380 ohm will be the current IL. So, Vz by RL 10 volt divided by 380 gives 26.32 milliampere is IL current. Now, what is the current Iz? Iz equal to I minus IL. So, I minus IL, I is 45 we have found out, IL is equal to 26.32 milliampere, that gives 18.68 milliampere as the Zener diode current flowing through the Zener diode. So, all the currents have been found out in part A, whatever we are asked. Second part, determine the value of RL that will establish maximum power dissipation, that is 400 milliwatt in the diode. So, in part B, that means you are given that the power dissipation in this Zener diode is maximum, which is 400 milliwatt. And what is this power dissipation? Vz into Iz. Vz is 10 volt, that is Zener voltage constant. So, that Iz max we can find out, Vz is 10 volts. So, Pz max divided by Vz will be the Iz max, the maximum Zener current that flows in the Zener diode, and that is equal to 400 divided by 10, that is 40 milliampere. So, when the Zener diode current is maximum, then obviously this current will be minimum, since this is constant. So, that minimum load current we can find out, which is equal to I minus Iz max. I is constant, which is 45 milliampere, we have already found out in part A. 45 minus Iz max 40, that gives 5 milliampere is the load current. So, the load current we know, the voltage across this load is nothing but Vz. So, VL is equal to Vz. So, that load resistance we can find out. So, load current 5 is equal to Vz by RL, Vz is 10 volt, RL we have to find out. So, RL is equal to 10 by 5 is 2 kilo ohms, since 5 is in milliampere, it will be order of kilo ohms. So, we get 2 kilo ohm load resistance, for which the maximum power dissipation will occur in the Zener diode. So, this is one example where we have seen that you have this constant voltage drop, and that will not change even the under the condition that maximum Zener current occurs, which is we have got in this particular case 40 milliampere. So, maximum power dissipation is 400 milliwatt. For that we have found that load resistance which will cause that maximum power dissipation 2 kilo ohm. Similarly, another problem we can try is that for this circuit where the load resistance is variable, find the range of RL and IL, that is what will be the maximum and minimum values of RL that will result in the load voltage being maintained at 10 volt. And second part, determine the maximum wattage rating of the diode. So, for the first part, in order to solve the first part, let us draw the circuit again. This is 1 kilo ohm and this is the Zener diode, reverse biased, because this voltage is plus minus 50 volt, is not, yes, Vi is 50 volt, and this is the load resistance which is variable RL. This is the Zener diode having the rating of Vz is equal to 10 volt, and Iz max is given, Iz max equal to 32 milliampere is given in the circuit. Now, this will be the load current IL, this is the Zener current, and this is the IR current. Now, first of all, whether the Zener diode will be turned on or not, that we have to find out. So, Vi into RL by R plus RL, R means this one is R. So, that is equal to 50 into RL minimum, that we have to find out what is the minimum resistance in the load that will be causing the Zener diode to turn on. Then 1 kilo ohm is R, let us keep it as in kilo ohm order, the final answer will be that will be in volt if resistance is in kilo ohm, and current will be in milliampere, RL minimum. Now, that should be equal to what? The Zener voltage, that is 10 volt. that is the limiting condition. In fact, this should be greater than 10 volt. Now, for this limiting condition, what will be the VI, what will be the RL minimum? That can be found out if we cross multiply 50 into RL minimum equal to 10 plus 10 RL minimum. So, 50 minus 10 is 40, 40 RL minimum is 10. So, what is RL minimum? RL minimum is equal to 10 by 40 gives 0.25 kilo ohm. 0.25 kilo ohm should be the minimum resistance of this load in order to cause Zener to break down, and for that condition we will get maximum load current, and maximum load current is VL by RL minimum. VL is nothing but 10 volt VZ RL minimum. So, 10 divided by, we have found out 0.25 kilo ohm. So, that gives 0.04 ampere or 40 milliampere. 40 milliampere is the maximum load current, and for maximum this is the minimum RL. Minimum RL we have found out to be 0.25 kilo ohm or 250 ohm, and for maximum condition, for maximum RL, IL is minimum. So, IZ will be maximum. So, what is that IZ maximum? That is given in your rating, IZ max equal to 32 milliampere. This is the rating of the diode, it is given. So, for that particular IZ max, we can find out what is IL mean, because IR is equal to, if we consider this current IR, VI minus VZ by R. So, VI minus VZ by R. So, VI is 50, VZ is 10, R is 1 kilo ohm, that gives you 40 milliampere. So, what is the IL minimum for that maximum load resistance we have to find out. So, IL minimum for maximum IZ, that is IR minus IZ max. IR is equal to 40 and IZ max is 32, 8 milliampere. So, 8 milliampere is the minimum load current. So, correspondingly we get RL max. So, RL max is VZ by IL min. VZ is nothing but VL. VL is load voltage across this resistance. So, that is equal to 10 volt divided by IL min, we have 8 milliampere, that is 1.25 kilo ohm will be the maximum load resistance. That means, you get for this two conditions of minimum load current 8 milliampere, maximum load current 40 milliampere, we get constant voltage VZ, which is 10 volt. Now, second part, B part is maximum voltage rating of the diode, maximum wattage rating, not voltage, maximum wattage rating of the diode is to be found out of the Zener diode. So, what is the maximum wattage rating? It is given by VZ IZ max. VZ is 10 volt, IZ max is 32 milliampere, we have been provided in the data sheet. So, 320 milliwatts will be the maximum power rating of the diode. So, in this way we have seen the application of a Zener diode in a voltage regulator circuit, and the Zener breakdown phenomenon maintains a constant voltage drop across the Zener diode at the Zener voltage VZ. So, we can have a constant voltage across a load resistance even when the load resistance varies, that means the load current varies, or there is a change in the input voltage, because input voltage may change, there may be fluctuation in the input voltage, which we face very often in our domestic household applications. We see that the supply voltage varies. So, even though supply voltage varies, we can maintain almost a constant voltage across the load, and that is the major advantage which this special purpose diode known as Zener diode has, and that phenomenon is very effectively utilized in voltage regulator circuit.